Hey there, welcome back to the channel, and we will continue in the problem solving sessions. So we were solving problems of CSES problem section, CSES set, and we were solving graph algorithms. And in the graph algorithms, so far we have solved a couple of problems, I think up to round trip. Now the next problem in the set is monsters. So in this video session, in this problem solving session, we're going to be solving this problem that is monsters, right? So I hope you're learning new problem solving techniques. Although so far we are just using depth first search or breadth first search, but you must have learned something like how to track parent, how to find a cycle, these type of things, how to keep the visitor nodes, how to check if a node is visited or not. Uh, these type of things we have learned so far, and these learnings, believe me or not, these learnings are going to help you somewhere when you will solve problems in a contest. These things are going to help you there, right? So without wasting any more time, let's jump to the problem solving part, and we're going to be solving this problem monsters. So let's jump to that. Hey there, so welcome back. So let's continue in the problem solving, and we will solve this problem that is monsters, right? This is the next problem in this graph algorithms section which we are solving, and we're going to be solving this problem here. So this problem is actually a little bit different from the problems we have solved so far. So far we have used depth first search and breadth first search in a very normal way. But here we have to modify our breadth first search a little bit. Let's see how. So in this problem, you and some monsters are in a labyrinth. Labyrinth is something like a maze, maze. When taking a step to some direction in the labyrinth, each monster may simultaneously take one as well. So you and some monsters are present in a maze or a grid of dimensions n cross m. Now in each second, you and monsters simultaneously move one step ahead. Like one step ahead means move to the adjacent cell. From one cell, from the cell on which a monster or you are, you can move to one of the adjacent cells if that cell is empty, right? Now your goal here is to reach one of the boundary squares without ever sharing a square with a monster. Sharing a square with the monster means you want to find a path to reach one of the boundary squares. So what is a boundary square? A boundary square is the one where there is no cell ahead of it or below it or above it or behind it, right? So for a cell to be a boundary cell, it should be either towards the leftmost part of the grid, it should either be towards the rightmost part of the grid, or at the top of the grid, or at the bottom of the grid, right? That is a boundary cell. So you have to start from the position where you are, and you want to reach one of the boundary locations without sharing any cell with the monster. Condition is that at each second you can move to adjacent cell, adjacent empty cell, and the monster can also move to the adjacent empty cell. The rules are same for you and the monster. So you just have to devise a path to reach the boundary cell without ever encountering a monster in your path. That's your problem, right? Now maybe the monsters, since the monsters are more than one, and there are walls in the grid, so in a grid, hash represents a wall, this dot represents a floor, a represents the start, m represents the monster, right? N and m represents the height and width of the map, okay? And you are supposed to reach one of the boundary squares without ever sharing a square with the monster, okay? Now print yes if the goal is possible and no if the goal is not possible, okay? So let's see how we can do that. Let's take this example. सेम एग्जाम्पल है क्या? नहीं, अलग है, राइट. So this is your maze, this is your n, and this is m. This is your maze. Here is a monster, here is a monster. So let's mark the monsters by red. Monster, a monster here, a monster here as well. So now in this fashion you have monsters, and here you have you, okay, the hero of the story, okay, and these are the villains, you know. Now here what you can do, you have to, so the monster can also move one step ahead, and you can also move one step ahead, right? Now let's keep it as it is, and let's not change it. Now what you will do, how would you solve this problem? Now can you see any way for yourself so that you start from here and you can reach one of the boundary cells? So what are the empty boundary cells? This is a empty boundary cell, this is a empty boundary cell, that's all. So can you reach this cell? Yes or no? Yes, you can. Now in one step A will move to here, A moves here, so A is no longer here. Now A changes its position to this position. Now in one unit of time, since A is moving from here to here, monsters will also move. This monster can move. Now how many options this monster have? This monster can move here, this monster can move here, and at the same time this monster, so this monster has two options, right? Let's say monster, so the monster, let's say, moves here, in this monster moves here, okay. This monster has two options, either this monster moves here or moves here, right? So let's say the monster moves here. This monster again has two options, this and this. So let's say this monster moves here. Here you have the monster, so you copy the monster, monster is here. Now here you have dot. So this is the motion of these monsters and the hero, okay. This is the motion of monsters and the hero. Now monsters has four possibilities, and the possibilities are not predictable. The monsters can have mood to move in any direction where he can, right, where the monster wants to move, right? So let's explore the worst possibility, where the monster and the hero may land in the same cell. Is there any such possibility here? Think about it. Is there any such possibility where, starting with this configuration, the monster and the hero can land at the same cell? Think about it. There are some possibilities, but obviously let's say A moves here and A moves here. So A, in 1 second, let's say A moves from here to here, and this monster in the same second moves from here to here. So monster and the hero land at the same cell. There is a possibility, but we will not pay attention to that. Just figure out a way for the hero to reach this cell. Is there any way? And the answer is yes. Move the hero from here to here, okay. Then from here to here, then from here to here, and here you will have a dot. Now from here to here, right? Then from here to here. So this is a way the hero starts from here, moves towards right, then moves down, and then again 1 unit to the right, and reaches the boundary cell, right? Reaches the boundary cell. So there is a possibility. Now this monster can't can't deviate, or can't, let's say, can't block the way of hero through this path, right? Because here you have wall here. You can see there is a wall here. So from here the monster is not going to stop the hero. And even if the monster chases the hero, even if the monster chases the hero and the hero simply continues along its path, the hero is going to reach the boundary cell. The monster will not be able to catch him, right? Or maybe, right? Because both are moving with the same speed, right? So for this the answer is yes. For this the answer is yes. There is a possibility. Move the hero towards right by 2 units. So the hero moves here, then down, and then 1 unit right. Hence the answer for this test case would be right, then down, then right. This is one of the possible ways for the hero to reach the boundary cell. Now this may not be the only answer. There can be multiple answers. The only condition that should be met is the hero and the monster should not land in the same cell at any moment of the path of the hero, or at any point of the path where the hero is walking. That's the condition. We are not bothering about the length of the path, we are not bothering about the direction the hero took. We just bother about whether the hero should not land in the same cell where the monster is present, right? Simple as that. Am I right? Yes. Now your plan has to work in any situation, even if the monsters know your path beforehand. So what's the way, how can we solve this problem? Can you predict the most optimal path for the hero? Think about it, pause here and try to think if you have any idea, any heuristic algorithm where you can actually predict the path of the hero. I don't think so. You don't have it, right? It would be very hard because the grid is unpredictable. You have to, either you have to process the grid beforehand in order to plan the path of the hero. But there is a simpler solution. Why? Just think about, take a look at this grid length. The grid length is n into m, so it would be 1000 into 1000. The highest dimension the grid or the maze can have would be 1000 into 1000. 1000 into 1000. And also there are some cells which are blocked here. The hash cells are blocked. There are walls here. So the only cells which where the hero can move are the cells with these dots. So this gives us an idea of brute forcing the solution. Brute forcing the solution means the most simplest form of the solution is the brute force solution. So what would be the most simplest form of the solution? That would be exploring all the possible paths for the hero. How? So hero is, let's say, at a position I, j. Now try moving the hero to all the possible situation or possible positions. The hero can move to I plus 1j. The hero can move to I j plus 1. I think I have written it wrong. I j plus 1 is this, and this is I plus 1j. I is the row, j is the column. And the hero can also move here. That is I j minus 1, right? Then from here I moved here I minus 1 and then j, right? So in this fashion we have these cells. This is the motion of the hero, the possible cells the hero can move. The hero is here, it can move ahead, it can move back, up, down, back, forth, up, down, right? This is how the hero can move. Then same goes for the monsters. Monsters also have this type of freedom to move in all the 4 directions where there is no wall. So how would we handle such situations where now the hero has the single source, right? Hero starts from a single position and moves. but there are multiple sources for monsters. Why? Because there are multiple monsters and they are also moving. So in 1 unit of time, the monsters also changes their position, and all the monsters changes their position, not a single one. So how are you going to handle that? Think about it. How do we handle a single source thing? So we have a single source and we move to its adjacent cells, and then we keep on repeating the process. We do it using a queue. We do it using a queue data structure. So usually we use a queue data structure to perform BFS, breadth first search. So we basically push the starting position. So now we have to perform the BFS here. BFS for the player and then BFS for the monsters as well. So how many positions the monsters have? 3 positions. This position, and this position. Which one this position is? So this is row number 0. This is row number 1. So 1 and 1. This is position number 1. So in the first queue, let's call it monster queue. Monster queue, let's say it's a capital Q. So in the capital Q, in the monster queue, we will have the first source as 1 1. Right? The first source is 1 1. Then the second source that we have is this. This would be 2 0 1 2 3. 2 3. So second source is 2 3. Third source is this 0 1 2 3. So 3 1. 3 1. This is the third source. So these are the 3 sources in the queue, in the monster queue that we have. The starting positions where the monsters are starting. Right? Now, anything else to say after that? So this, so we will use a monster queue. Let's call it a monster queue. Monster queue to perform BFS 1. Right. Then second is your, what is the second thing? Distance. You also need a distance grid or distance matrix to track the distance of each monster from its source. Now this is the source of first monster, this is the source of second monster, and this is the source of third monster. And then we also use a distance matrix of the same dimensions as the dimensions of this grid. So we will use a distance matrix to track the distance of each monster. Let's call it monster dist. And x comma y represents the this represents the minimum distance, or we can say minimum time for the monster to reach cell xy. So that's the minimum time any monster can reach this cell x and y, right? Minimum time for the monster. Now this is not a specific monster, it can be any monster out of these 3 monsters, right? That's second point you have to keep in mind. This is what the monster matrix you will have, right? And that's all. You perform the BFS, and this type of BFS is called multi-source BFS. What is it? It is called multi-source. This is your multi-source BFS. So if you don't know what is multi-source BFS, you want some more knowledge and background for that, need some data, you have some internal urge to solve a couple of problems before you try your hand on this problem, then you can go back and learn multi-source BFS. Maybe use some website like CP algorithms or so, or maybe read from GFG, and then come back to the problem. Although it's not something it's not an entirely new concept, but the sources are changing. So usually in a BFS we have single source, here we have 3 sources, rest everything is same. Okay, and this is your monster matrix which you have to keep in mind. And that's all. When you perform the BFS, so how do we start? We start this queue, Now from the queue, pop these elements, pop this node, pop this cell, then pop this cell, then pop this cell, and then move to the adjacent cells, move to their adjacent cells. Now this monster is open to move here, here, two open positions, right? This position is 1 2, this position is 2 1. So we will push those cells here. So when you pop this cell out, you also pop at the cost of 1 comma 1, you will push 1 2 and 2 1. You will push 1 2 and then 2 comma 1, right? Like that. And you will also update the distance for 1 2 and 2 1 in the matrix. So the matrix will look like this. So initially this cell contains 0. So these are at infinite distance, let's call them infinite, or let's say I n I n, right? And copy this thing here, copy it here, and the second in is, you know, empty cell, and here we have again in 1 2 3 4 5, move it here. Now since I pushed these 1 1, I pushed 1 1, so at 1 1 I would have 0 at the starting, then at 2 2 4 here, 2 not 2 3, it's not 2 3, I think 0 1 2 3 4, it's 4 not 2 3, sorry. So it's 2 4. So at 2 4 we would have 0 0 1 2 3 4, here we would have 0, then we would have 0 at this point as well, that is 3 1. So 3 is this and 1 is this, so here we would have 0. Now since I moved from here to these adjacent cells, so the distance here, which is 1 2, which I pushed here, and 2 1 will become 1. So here it would be 1, here it would be 1. So in 1 second the monster can reach this cell, in 1 second the monster can reach this cell, right? So for the monster it's just going to take 1 second to reach these cells, right? Now this thing you have to keep in mind. Right? So क्या हो गया so here we will have to, you know, move ahead, okay? So from here 0 1, so it takes only 1 second to reach this cell, it takes only 1 second to reach this cell, right? Now here we will have 0, then again from here I can move here, here and here. So we have 3 positions to move, this position, and this position. So we have 3 positions to move from this cell. So from this cell in 1 second, here we will have 1, here we will have 1, and here towards the left of it we will have 1. So what about this second monster, this monster? This monster can move to this position or this position, right? Now at this position we already have 1, so it's not going to change anything. So but at this position infinity will be changed to 1. So in this fashion, and how many cells will be pushed here? Now this cell, this cell, this cell, this cell, this cell, so 1 2 3 4 5 6 cells will be pushed in the queue. So that's how the queue is actually working, that's how the queue is working and updating the distances in this matrix or monster distance matrix, right? So this matrix at the end, when we have processed all the cells, will give an idea for each cell that how much minimum time the monster is going to take to reach that cell. That's all. Once this thing is clear, we are free to choose the moves for the hero. that we have, right? The hero is starting from here. 2 3 4 5 6 7 8 5 6 7 8. So the hero is starting from here, from here. Here our hero is. And we will have another matrix for the hero. We will create another matrix for the hero, and that matrix will be similar to this matrix, again distance matrix. But now in this case the source is only one, so we will just need a single source in order to perform BFS. Let's take a, for for the player turn. So when the player starts its motion, player starts his motion, we will have a queue for the player, queue for the player would be, let's say, queue. And in this queue I'm going to push the starting cell, that is this, which is 0 1. So 1 0 1 2 3 4. So 1 comma 4, 1 comma 4. 1 comma 4 is the starting cell for the player, right? It's the starting cell for the player, right? Then what else do we have here? We have this starting cell, and then we also have the second thing that we have is distance matrix for the player. Let's call it min distance, and min distance xy again is going to give me the minimum time for the hero, for the player to reach cell x comma y, right? Now this is a single source BFS, and pop this cell 1 comma 4, pop this cell 1 comma 4, and move to its adjacent cells. Again a similar matrix for the player, update the distance, and we will again have a matrix for the hero as well, for the player as well. And there we just have to check whether while performing this BFS, this second BFS, if you are reaching the boundary cell. So third thing that we have to keep track here, check for the boundary cell. So which one is a boundary cell? A boundary cell is the one when the x is either equal to, this x is either equal to n minus 1, or x is equal to 0, or y is equal to 0, or y is equal to m minus 1. So if you found any of these four conditions to be true, then that cell is the boundary cell, and you're gonna put that, let's call it a escape cell as that particular x comma y, right? That is your escape cell. Now if you never encounter this escape cell, then the answer is a simple no. You can't escape the matrix, and the monster is going to kill you somewhere, right? If you find this escape cell there, and if you find this escape cell, means there was a way out, and for that you just have to print the path. Now how would you print the path? The next question. One thing you also have to keep in mind is, one condition that you have to keep in thing is, that condition is this monster distance, for any x comma y, the monster x y, for any cell x comma y, this monster distance element should be strictly what? Should be strictly what? Less than. Should be strictly less than this min distance xy. Why? Means this monster, not less than, sorry, should be greater than. Means the monster takes greater time to reach the same cell than the hero, right? The hero should first reach the cell and move ahead, then the monster can arrive at that point. The monster should never reach the cell before hero. That's the condition we should follow. We have, so the monster distance or the monster time should be strictly higher. That's the second condition that you have to keep in mind. This was the first condition, and this is the second condition that you have to keep in mind while performing BFS for the player turn. Right? Now you see how we are using the data from the previous calculations here in these second calculation, right? And once you process the entire matrix and you complete the second BFS, this second BFS, you will have your escape cell prepared. If this escape cell is null, it doesn't contain anything, means the answer is no. If it contains something, then means there is an answer. But now you also have to keep track of the path where the player is moving, and for that you will need one more matrix. You will need one more matrix, and that is, let's call it path matrix. So path now we have reached the fourth step here for the player is to track the path. So while we are moving, while we are making the moves, we also have to keep track of the path. So what is this path xy matrix? This path, we will use one more matrix, that is a path matrix, right? This is a path matrix where path xy represents the step taken at cell x comma y, right? Now the step can be a up move, it can be a down move, it can be a left move, it can be a right move. Okay, right? Either U, D, L, R. One of the four moves we would have, right? One of the four moves we would have. Now I hope it is clear to all of you people how we are actually moving here. And now what we're going to do is we will be implementing this algorithm. We will be writing a code for it, right? So how would we know how we track the path. You know how we track the path. If we have made a move of U, then at path xy we're gonna store U. Okay, like from xy, if I have moved up, then I will store U. U means I have moved up. Okay, is that okay? Is that fine? Or I think I'll have to, if I'm making a move of up. Making a move of up means moving from I comma j to I plus 1 comma j, right? I plus 1, no? Not I plus 1, it's I minus 1, right? From I comma j, I am moving to I minus 1 comma j. That's a up move. That's a up move. So I want a path. So for the new cell, what I'm going to store is, for the new cell, if I want to store the previous, so from here, if I want to reach the previous cell, then I'll need a down move, and from ij, if I want to move to I minus 1j, then I'll need a up move. So at this point, I'm going to store U. Cool? Fine. Or we can also do it like this. The last step taken, we can also represent it like this. Last step taken to reach cell x comma y. So if I am reaching from I comma j, I am making a up move to I minus 1 comma j. Then in order to reach I minus 1 comma j, what last step did I take? It was up u. That we can think of it like this as well. The last step taken to reach cell xy, that is up. Okay. So yeah. Okay. That's all. And I hope we have all the pieces, and now we just have to gather them and convert it into a working solution. Let's jump to the implementation part. What's the problem? It's monsters, and we have n and m, and then we have, first we have n and m, and then we will have to read a grid. So let's read a grid. Let's read a grid like grid. Okay. Vector of vector, not int, vector of vector char. Okay. Grid n vector, and here you will have m. Now iterate for all the rows, then for all the columns, then read grid I j, and then why we have a red here? It's not int, it's char. Okay. Now from here, what you're gonna do is you're gonna use a queue. So let's perform BFS for monsters. Use a queue of pair. Let's call it capital Q. Capital Q dot push. Now iterate over each cell which we have recorded for int j0 j less than m j plus plus. Now if grid of I j is equals to a monster, then what you're gonna do is you're gonna store that pair I comma j in the queue. Simple, right? And we will also need a, remember the distance, monster distance of dimensions same as the grid, m0, not 0, very large value. Let's take int max. Okay. And here for this monster distance for I and j, I'm gonna say 0, like the monsters are starting from that point. Once you have this queue prepared and the monster array there, you can perform the BFS while the queue is not empty. You pop the top pair, let's call it cell, which would be q dot top, not top, front, and pop it out of the queue. Now you move to the adjacent cells, right? Now we also need the direction vectors here, vector dx, or we will say dr to be more specific, 1 0 minus 1 0, vector int dr dc 0 1 0 1, right? Minus 1. So what does that mean? This like 1 0 means I'm moving 1 unit along the row, means down. So this is like down, then 0 and 1, 0 in row direction and 1 along the column direction means I'm moving right, and minus 1 0 means I'm moving up, 0 minus 1 means I'm moving left. So down, down, and then right, then up, then left. So it's an anti-clockwise. This is anti-clockwise direction, है ना? Now I'll iterate over these 4 directions. So new cell would be, new row would be, it would be cell dot first plus what. Now here we'll also have to check if this cell contains 0. Yes, that's fine. And do we have any condition here to check? No, I don't think so. Now the new cell, the adjacent cell would be cell dot first plus the direction dri, and the new column would be cell dot second plus dr or dci. Once you have that, what you're gonna do? So I move to the adjacent cells, and then where would we move? We'll have to check if these cells are valid or not. NR should be greater than equals to 0, and NR should be less than N, and NC should be greater than equals to 0, and NC should be less than M. If that is the case, then what? This would be new row and new column. And what would you do at new row and new column? You'll have to update the distance. Now we also have to check if since these are valid cells and the grid NR and NC is not equal to hash, and it's not equal to hash, as well as it's not equal to A. Grid NR NC is not equal to A, as well as this cell is not visited, so we'll also need a visited matrix. We have forgot to draw that. Let's call it visited and vector bool. Maybe you are not getting bored here. If you are getting bored, then try coding it yourself. You will not get bored. And it's also not visited, right? And since it's not visited, here you'll have to mark them visited. I and J has to be visited, and then here mark them visited, NR NC mark them visited, and also push the NR and NC, okay, in the queue. Now do we have anything else to say? Okay, so do we have anything else? Move to the adjacent cells. Anything else? 9. And you will also update the monster distance for NR and NC as min of monster distance NR NC with monster distance, the parent cell, which is what? Cell dot first, cell dot second, like that. Is that fine? Yeah. Now this thing is clear, and we have completed the BFS. I hope nothing is missed out. Am I doing it right? Monster, ठीक है. That's fine, that's fine, that's fine. Distance matrix, we're done with this. Okay, I think I'm doing it okay. And yeah, now let's move to the you know that player thing. Let's move to the player turn, now we'll also use one more queue for the player as well. We will have to use one more queue for the player, and iterate over the matrix. So let's make it a separate thing, player turn, right? For int j less than m, j plus plus, if grid of ij is equals to the player turn, which is what's the player turn? The player turn is a, and if that's the case, then you're gonna push that cell I comma j, and here you will also have the vector for the player distance n vector m 0, not 0, infinite int max, and here you will also have that distance for this cell to be updated. Distance for I and j in this case will be 0. Now again run this DFS for the player, and that would be q.front. Pop this node. I'm assuming you know the BFS, how to perform the BFS, right? I am assuming that you people know how to perform the BFS, right? And so it's just a plain BFS, nothing else. And now move to the 4 directions. New row would be cell dot first plus DRI. New column would be cell dot second plus DCI. Okay, so if this new cell is valid, first you have to check if it is a boundary. If it is valid and boundary cell, so if nr is greater than equals to 0, and nr is less than n, and nc is greater than equals to 0, and nc is less than m, and grid is not equal to hash, and visited nr, and not this is visited, right? it's not visited. And if that is the case, here you're gonna ask yourself that question, if since this is a valid cell, and then you'll have, if this is boundary, if this cell NR and NC is boundary cell, then that means you have reached the escape. So this is your escape, not I, NR and NC is your escape. So let's create a pair here as well. The pair is escape pair, escape pair. It contains -1, -1, right? And here you're gonna reinitialize it. Now this is fine, and if this is valid, then we will break out of the loop. Okay. Otherwise, what you're gonna do, you also have to check whether, since this is a valid cell, if distance for NR and NC is not equals to infinity, means it has already been calculated. You're gonna continue to the next cell, right? It's not equal to int max, right? Now I hope it's fine, I haven't missed anything. One more thing that I'll need is a path, vector of vector, not int, char, path Now this path matrix is going to store the actual path. So if your I is 0, that means, and you have reached this point, you also have to update. Now here you also have to check if the distance, if the monster distance for NR and NC is what? If the monster has arrived there first, then it's not possible. So if it is less than equal to, this time is less than equal to distance of NR NC, then you're gonna continue. Before that, you also have to distance of NR is equals to distance of N, we will say cell dot first, second, plus 1, right? So if I is 0, means you are making that move. Which move? If I is 0, means the move is a down move, so it's a down move. So for this move, what you're gonna store for in this path array, path of NR and NC, you're gonna store this D. If I is 1, path of NR NC, you're gonna store what? You're gonna store R. If I is equal to 2, then path of NR NC, you're gonna store DRUL, right? U. If I is equal to 3, path of NR NC, you're gonna store L. Okay. Now once you have these pieces here, you're gonna have the string answer here. Now here you also have to check if your escape still contains -1. If that is the case, means you couldn't find the escape point. So the answer is no, and I'm gonna return right from there. If not, then the answer will contain something, then you have to start from the escape point. So you will have a start point as auto escape auto, let's call it current will be initialized with escape. Now the current should not be equal to what? Should not be equal to, what we would say, the starting point. So we'll also have to store one more thing, pair start, right? So just here when you are pushing for A, you also push for start I comma J, right? So until this current is not equal to start, the current will be updated with current dot. Yeah, you need one more thing, that is you have to track one more thing, that is parent vector of you know vector int parent vector of pair parent. You will have to track for that, and vector of vector pair n vector pair m. Now here you will track the parent, right? If I'm not wrong here, this for this, then for this, then for this, parent vector pair sorry, like this, a vector of I was confused. Okay, so we'll have to track that parent here as well. Parent of nr and nc was cell dot first comma cell dot second, right? And current dot first would become parent of current dot first dot first, like this, right? And here what you're gonna do is you're gonna add the this what was that move taken a path of current dot first and current dot. I know that this is a little bit lengthy. Now you have to reverse the path. Why? Because I'm tracking the moves in the reverse direction, so I'll have to reverse this answer. So let's reverse. And finally print yes, and in the new line print then print the answer, right? So this is how it's gonna work. So let's try submit it. So this code is working finally, and I've made a few changes here. Like the most crucial condition that you have to check is this thing, player must arrive before the monster. Rest everything is same. You don't have to change much. It's just an easy thing, keep it really not a big thing. And the code is actually lengthy. It's not hard, but it's lengthy. and it may become hard to debug if you haven't solved enough such problems. Like if you have solved enough such problems, if you have coded enough solutions similar to this, uh, what are the bottlenecks, or what are the points, the potential points where you may have an error. Usually the error is here when you check these conditions, when you make these distance updates, when you during this path tracking, again these boundary conditions. These are the points where you may make mistakes, right? And yeah, so I'll recommend you to try to code this solution by yourself from scratch. You people will learn a lot, you know. And let's try submitting it. Got accepted, and I hope the thing is clear to you. Now let me know if you have the video is really getting long and long, so I'll pause here and I'll see you in the next one. Till then, take care and bye bye. And if you have any problems with the multi-source BFS, then you please go and first learn multi-source BFS, then come back to the solution. And I'll see you in the next one. Till then, take care. Bye bye, ladies and gentlemen.